Look at active industrial switchgear with the naked eye, and failing high-voltage components look perfectly functional. But through a thermal imager, structural anomalies glow white-hot. But thermal cameras do not actually see heat. They detect and quantify electromagnetic radiation, the waves emitted continuously by the thermal motion of molecules inside every physical body above absolute zero. Treating these devices like standard visible light cameras in an industrial or tactical environment guarantees catastrophic measurement errors. The hardware and the raw digital data it captures are strictly governed by absolute thermodynamic laws. Without rigorous mathematical and physical correction by the operator, the raw voltage read by the sensor is useless. Capturing accurate radiometric data requires mastering the entire chain of custody, from thermodynamic first principles to microbolometer MEMS architecture to strict field calibration protocols. The bedrock of infrared thermography is Planck's radiation law. It governs the spectral distribution, wavelength dependency, and maximum power density of a target's thermal emission. Integrating Planck's equation yields the Stefan-Boltzmann law. This defines the exact relationship between energy and temperature. The total emissive power of an ideal blackbody is directly proportional to the fourth power of its absolute temperature. But knowing the total power isn't enough to build a camera. Wien's displacement law dictates that as an object's temperature rises, its wavelength of peak emission shifts inversely. This chart plots a black-body curve for an object of 30 degrees Celsius, peaking near 10 micrometers in the long-wave band. But for a heated industrial surface at 1000 degrees, the peak shifts dramatically, spiking near 2.3 micrometers. These shifting emission wavelengths dictate the optomechanical design of all thermal cameras. Engineers must build entirely different sensors to catch specific waves. The immediate physical hurdle is the lens. Standard silicate window glass is opaque to long-wave infrared radiation. It absorbs and reflects thermal energy, acting as a solid barrier instead of a window. Thermal lenses must therefore be manufactured from highly transmissive, specialized materials like germanium or zinc sulfide. Even with specialized optics, the camera must combat atmospheric attenuation. Over distance, suspended water vapor and carbon dioxide physically absorb and scatter the infrared signal. To avoid this scattering, systems target 3 atmospheric windows: shortwave, midwave, and longwave infrared. Thermal optics operate under entirely different constraints than visible light cameras. They are built as strict, selective filters designed to capture only the specific infrared wavelengths that survive the journey through the atmosphere. At the sensor level, architectures divide into 2 distinct categories: cryogenically cooled photon counting detectors and uncooled thermal microbolometers. Modern uncooled cameras utilize a focal plane array. This requires extreme physical miniaturization to fabricate microelectromechanical systems, or MEMS, directly onto a silicon substrate. This diagram shows a MEMS microbolometer pixel. The vanadium oxide membrane is suspended across a vacuum. Infrared energy passes through, bounces off the titanium mirror below, and redirects upward. Thin isolation legs support the membrane, preventing heat from bleeding into the circuit. As the vanadium oxide membrane absorbs energy and heats up, its charge carrier mobility increases. This causes a precise, measurable drop in its electrical resistance. The system quantifies this using a charge transimpedance amplifier, comparing the active pixel's current against a blind reference bolometer shielded from incoming radiation. An uncooled microbolometer does not see radiation in the traditional sense. It functions as a microscopic mechanical scale, measuring tiny fluctuations in physical electrical resistance caused by photon absorption. Because these MEMS pixels possessed actual physical mass, their thermal response is bound by the strict rules of a first-order thermal system. This creates a physical delay known as the thermal time constant. It typically takes a modern sensor 8 to 12 milliseconds to physically heat up or cool down to match a target. This graph models a pixel exposed to an instantaneous 100-degree spike. The environmental temperature jumps vertically, but the internal temperature lags. If we stop at 10 milliseconds, a 100 frame per second exposure, the pixel only reaches 63 degrees, leaving a massive 37-degree measurement error. Under the laws of a first-order system, a pixel requires 5 full time constants to reach 99% of a steady-state temperature change. This physical mass constraint forces uncooled thermal cameras to operate at slower frame rates, typically 30 to 50 frames per second. Speed is intentionally sacrificed to ensure radiometric accuracy. In the field, hardware is only half the equation. Real-world materials are gray bodies. They emit less radiation than a perfect blackbody. Operators must manually compensate for this variable, known as a material's emissivity. Under thermodynamic equilibrium, Kirchhoff's law of thermal radiation states that a body's capacity to absorb equals its capacity to emit. For opaque bodies, this means low emissivity guarantees high reflectivity. When you point a thermal imager at a low emissivity surface, like polished metal, the camera primarily records reflected environmental radiation, including your own body heat. To isolate and measure this reflected background radiation, operators use the crumpled aluminum foil method. This flowchart outlines the protocol. Set the camera's emissivity to 1.0, place crumpled foil in front of the target to capture environmental radiation, and record its apparent temperature. This recorded temperature is inputted into the camera as the reflected apparent temperature variable. The internal processor uses it to mathematically strip the environmental noise out of the raw data. For highly reflective targets, operators must physically alter the surface, applying known high emissivity coatings like matte paint, vinyl electrical tape, or PCB lacquer to capture a true reading. The most advanced thermal hardware in the world will generate false data if the operator fails to actively correct for the target's physical material properties. These thermodynamic principles are codified into mandatory inspection workflows by standards like the ISO 18434-1 framework for condition monitoring. In heavy electrical settings like this substation, loose bolts and component fatigue create high contact resistance, appearing as localized thermal anomalies on an inspection scan. But ISO protocols strictly require that electrical systems operate under a minimum 40% electrical load during a thermal scan. Below a 40% load, high contact resistance fails to generate sufficient thermal contrast. Severe, dangerous faults remain completely invisible to the microbolometer. Industrial thermography standards exist because physical laws like thermal conduction and load-based heating cannot be bypassed by simply buying a more expensive camera. In the extreme operating environments of tactical firefighting and search and rescue, equipment is governed by the ruggedized NFPA 1801 standard. Operators in these conditions face unique visual hazards. Standing liquid water behaves as an opaque barrier, physically absorbing and dissipating infrared wavelengths. Cold water patches on a floor can trick operators into seeing false holes leading to a lower level, while smooth, wet surfaces can reflect ambient fires, masquerading as structural hotspots. To combat constant, dynamic environmental temperature changes, these cameras drop a mechanical internal shutter in front of the sensor to perform automated non-uniformity corrections, clearing fixed pattern noise from the array in real time. Thermal imagers are constrained by absolute physical boundaries. They cannot see through glass, they cannot bypass pixel mass, and cannot ignore target emissivity. Radiometric thermal imaging is a profound triumph of applied physics, but extracting truth from the invisible spectrum ultimately relies entirely on the operator's strict adherence to thermodynamic first principles.